Laboratory Management. Monitoring the Quality Control Program. Part 2. With MCQ quiz.
How choose appropriate control materials? The control material should 1. Be serum or whole blood based, in most cases. 2. Mimic substances, matrices, normally appear in patient specimens. 3. Contain assay values within both clinically significant ranges and decision concentrations for the measured analytes. 4. Fall within the analytical measurement range, AMR. 5. Have a minimum of 2 concentrations to adequately monitor system performance. 6. Demonstrate minimal vial-to-vial variability. 7. Be available in sufficient quantities to store and remain stable for some time, preferably a year, if they are serum-based controls. Blood-based controls are limited in longevity. 8. Be a unique product from the calibration material to allow for an independent assessment of performance. If calibrators must be used as quality control material, the lot number must be different from the lot number in use for routine quality control.
Liquid controls versus lyophilized controls. 1. Liquid controls are more convenient to use than lyophilized controls. 2. They require no preparation and could offer better reproducibility than lyophilized controls where a pipetting error may be introduced during reconstitution. However, liquid controls may require frozen storage. Careful handling and mixing post-thawing are required before use. 3. Lyophilized controls are serum, whole blood, or other specimens that have been freeze-dried under a high vacuum, low pressure. 4. These materials must be reconstituted before use. 5. This gives the potential for pipetting error. However, lyophilized controls can usually be stored for longer periods. Similarly, but for a different reason, lyophilized controls must be carefully mixed after the addition of the liquid for reconstitution. 6. Careful attention to verifying that all solid material is dislodged from the bottom of the vial and mixed to create a homogeneous solution. Assayed and unassayed controls. Monitoring analytic quality through the use of control materials involves the following: establishing target values and ranges, mean and standard deviation. Evaluating the control data based on the established limits. Initiating and documenting appropriate actions when controls exceed the acceptable limits. When new lots of control materials are first put into use, the process needed to establish or validate the target values depends on whether the controls are assayed or unassayed. Assayed controls. The analyte target values and ranges are specified in the manufacturer's product inserts. The assigned values must be verified in the laboratory. Unassayed controls. The manufacturer lists the analytes present in the control material but does not define acceptable ranges. The target ranges for these controls must be established empirically by analysis in the laboratory. One advantage to unassayed controls is they are usually less expensive than assayed controls.
For calculating control ranges, the laboratory may use assayed or unassayed controls. Each control lot will require the calculation of acceptable ranges for each lot of control materials. The first step in this process is to collect enough data to make the calculations useful. The selected control material should be evaluated with routine analytical runs. This allows for the inclusion of all normal and acceptable variations inherent in the test system. For the data to reflect future system performance, it is imperative that the measurements be made under conditions representative of the normal variation encountered during the course of daily testing. Possible variations in testing include: 1. Change of calibrator lots. 2. Performance of calibration. 3. Change of reagent lots. 4. Change of individual bottles of control material. 5. Operator variation. 6. Data variations throughout the day/shift. 7. Change in instrument parts such as probes or pipettes. 8. Changes encountered following a routine or unscheduled maintenance. Data should not be collected during situations not reflective of routine control testing or results. The number of collected data points is important. The greater the number of data points collected, the greater the representation of the true quality control values for the individual analytical system. All valid data points should be included in calculations. Otherwise, the calculated control limits may become too restrictive and not reflective of the actual test system variability. Compiled data should be reviewed in its entirety. Upon review, if more than 2 data points appear to be significantly higher or lower than the majority of the data, this could be indicative of a potential analytical problem. Prior to finalizing the control ranges, the problem should be resolved. Following the resolution of the issue, the data must be recollected and applied to the daily laboratory operations.
Setting the control range. 1. The control range must be established after the collection and analysis of data points. 2. The determination of appropriate quality control ranges is based on the means and standard deviations calculations. 3. Assuming system performance remains stable, the mean is an estimate of the reflection of the central tendency of the distribution of control values. It is an indication of accuracy. Under the same conditions, the standard deviation, SD, is a reflection of imprecision. For establishing the range for each control incorporates using the mean as a central value. 5. The range is then established by incorporating multiples of the SD, example, plus or minus 2 SD. 6. Each control range is set using the same numeric format for the analyte. 7. The quality control is reported as whole numbers if patient results are reported as whole numbers. 8. Values represented by decimals will include the same number of decimal points as patient results are reported. 9. If more digits are present, the rules of numeric rounding will be incorporated to achieve the correct digits. Using the mean as the central value, the upper and lower level of the range is set with plus or minus the chosen multiple of the standard deviation. Example. Glucose normal control mean equals 80 mg per deciliter. SD equals 6 mg per deciliter. Using a multiple of 2 SD, glucose normal control range is: lower range equals 80 mg per deciliter, 12 mg per deciliter equals 68 mg/dl. Upper range equals 80 mg per deciliter, plus 12 mg/dl equals 92 mg/dl. Then control ranges, 68 to 92. For each control, it is advisable to recalculate the mean and SD each month as data is added from previous months. The cumulative or lot-to-date means and SDs are used to update control ranges. This gives a more representative picture of long-term test performance. Configuring the control range. 1. Control ranges that are either too narrow or too wide represent data that will not reflect appropriate statistical evaluation to allow for the verification of the accuracy of the analytical system. Too narrow control ranges may lead to a high rate of control values being rejected when the analytical system is in control and performing accurately. 3. These incorrect assessments result in false rejections of quality control testing. For the 2SD control range, or 1-2S control rule, describes criteria where a run is considered out of control if a data point exceeds the mean plus or minus 2 SD. 5. As noted on the bell curve, statistically, this would occur only 5%, 100-95, of the time, even when the system is running correctly. 6. The chance of a false rejection would be low, and the chance of a value falling outside this limit due to a true problem is increased. 7. Conversely, ranges that are too wide may allow control values to be accepted when the system is truly out of control and may not be performing accurately. Control range is set at the mean plus or minus 1 SD. The frequency of data points falling outside the established range will occur more frequently than expected. 9. As demonstrated on the bell curve, 32%, 100-68, of the values would fall outside of a range this narrow, even when the measurement system is operating as expected. 10. This would represent a high rate of false rejections. False rejections occur when values fall outside of limits that were set for the purpose of signaling a change or problem with the measurement system when, in fact, there has been no change or problem with the system. 11. Ranges set at 3 SD, or 1-3S control rule, would be much more sensitive to detecting a true problem with the test system. 12 in this case, during normal operation, there is only a 1%, 100-99, probability that a control value will fall outside this range. Thus, this criteria is more specific in detecting a true problem with the system but, of course, would be less sensitive at picking up an actual problem that could impact patient test results. Verifying ranges of assayed controls. For assayed controls, laboratory personnel can use the target values from the manufacturer as guidelines for the initial verification of control ranges. 1. The laboratory must verify its mean by repeat analysis of the control material. 2. This repetitive analysis demonstrates that the quality control values fall within the manufacturer-supplied range. 3. For initial verification purposes, the SD may be provided by the manufacturer or derived from previous control lots. 4. To utilize standard deviations from a previous control lot, the previous control lot needs to demonstrate consistent stability over time, and the new lot of control materials must have target levels that are similar to the previous lots. 5. Another option is to initially establish limits based on SD information obtained through external QC programs, including proficiency testing programs or other peer comparison programs. Verifying ranges of assayed controls. The Clinical and Laboratory Standards Institute, CLSI, recommends collecting at least 20 data points on separate days if there is no previous history of QC data. The control material should be included as part of the routine analytical run for a long enough period that the expected variation in your lab can be observed. Collecting data over too short a period will give too small an estimate of standard deviation. The longer, the better, because the calculations will include such variables as 1. Method changes. 2. Performance achieved before and after maintenance. 3. Different operators. Note that it is important to periodically rotate QC testing among operators. 4. Changes in reagent lots. 5. Changes in sample probes or pipettes. 6. Calculations based on the observed means for the data collected should fall within the range stated by the manufacturer, and the mean and SD ranges should be evaluated periodically to verify they remain appropriate over the period that the lot is in use. Establishing QC ranges for unassayed controls. Unassayed controls are provided to the laboratory with documentation of the analytes found in the control solutions. However, because there are no predetermined target values and ranges for the unassayed control materials, the laboratory personnel will perform a replicate analysis of the control material to determine laboratory-specific target values and ranges. Control limits for each unassayed control are determined by running a replicate analysis. The laboratory is responsible for determining the number of replicates that will optimally demonstrate representative variation over time. The testing is performed in parallel with lots of quality control material with previously determined ranges. The higher the number of replicates, the greater the confidence in the determined ranges. Laboratories with high test volume or a component of a larger medical system with standardized instrumentation can benefit from sequestering the same lot of control materials and implementing a new control lot concurrently. This will allow not only the accumulation of larger amounts of data from the multiple facilities, but also significant cost savings with the volume purchase and the purchase of unassayed controls, which are less costly. Evaluation of this data can also serve to detect instrument problems if data from one instrument varies significantly from other instruments in the system. Choosing QC materials for qualitative tests that use a cutoff value. A laboratory may report some tests utilizing a qualitative result that is based on quantitative measurement. When this is done, the method uses a cutoff value to distinguish positive from negative results. A sample concentration at or above the cutoff value, as specified in the testing protocol, is reported as positive, and a sample concentration less than the cutoff value is reported as negative. Negative and positive quality control material employed for tests reported in this manner should be at concentrations that meaningfully confirm performance below and above the decision threshold for the analyte. For example, with drugs of abuse screening tests, the optimal controls would be a positive control that is at or above the positive/negative cutoff and negative control with a number near the cutoff, example, 25% below the cutoff, to maximize the detection of problems with the test system. Using a very high or very low control is less rigorous monitoring of quality than a control that is slightly above or slightly below the cutoff value. MCQ. Question 1. The laboratory has received a new lot of quality control. In reviewing the package insert, the supervisor cannot find the intended target and ranges. A list of analytes for each control vial is included. The quality control company's website reveals no additional information. What is the most logical explanation for this scenario? Please select the single best answer. 1. The control material is unassayed and no target values and ranges are available. 2. The control material is not FDA approved and is for research use only. 3. The control material is assayed and the manufacturer will provide targets and ranges upon request. 4. The ranges do not change with a change in lot numbers and the previous target values and ranges can continue to be employed. The correct answer is number 1. Feedback. Unassayed controls are provided to the laboratory with documentation of the analytes found in the control solutions. However, because there are no predetermined target values and ranges for the unassayed control materials, the laboratory personnel will perform a replicate analysis of the control material to determine laboratory-specific target values and ranges. Control limits for each unassayed control are determined by running replicate analysis. For assayed controls, laboratory personnel can use the target values from the manufacturer as guidelines for the initial verification of control ranges. The laboratory must verify its own mean target by repeat analysis of the control material. The assigned values must be verified in the laboratory. Question 2. The laboratory manager is selecting new quality control material for the chemistry analyzer from a new vendor. Which of the following represents an appropriate selection of control materials? Please select the single best answer. 1. The same as the current lot calibration materials. 2. Similar matrices to patient samples being analyzed. 3. Span the analytic range, plus 10% above the range on the upper end. 4. Minimum vial-to-vial stability. Feedback. Quality control material should consist of similar matrices, substances, to those that comprise patient specimens. Employing control material composed of a different matrix to patient samples may yield varying results. It is ideal if the selected materials do not vary from vial to vial, since large quantities of each lot are purchased and stored for long-term use. Ideally, the control material should not be the same as the calibrator material. However, if appropriate quality control material is not available, the calibrator material may be used if a different lot number of the calibrator from that in use for calibration at the current time is available. All results should be within the analytic measurement range, AMR, for the quality control material. The chemistry laboratory is collecting data to validate the manufacturer's assay range for a new lot of control material. The testing was run in parallel with the current lot of quality control material. When data is reviewed, it was noted that for the normal control, 4 data points out of the 25 points were significantly lower than the other data points. Which of the following represents an appropriate action for the data represented by these points? Please select the single best answer. 1. These data points should be discarded as they are random. 2. Evaluate analytic procedures for an analytical problem. 3. Include the points in the data calculations. 4. Adjust ranges based on these low data points. Feedback. As required, the new control material was evaluated with routine analytical runs. This allows for the inclusion of all normal and acceptable variations inherent in the test system. The number of collected data points was appropriate. The greater the number of data points collected, the greater the representation of the true quality control values for the individual analytical system. Compiled data should be reviewed in its entirety. Data that is an outlier to most data points should not be eliminated. However, ranges should not be calculated based solely on these low points. All valid data points should be included in calculations. This allows the resulting data to reflect the actual test system variability. Upon review, if more than 2 data points appear to be significantly higher or lower than the majority of the data, this could be indicative of a potential analytical problem. Before finalizing the control ranges, the problem should be resolved. Question 3. The chemistry laboratory is collecting data to validate the manufacturer's assay range for a new lot of control material. The testing was run in parallel with the current lot of quality control material. When data is reviewed, it was noted that for the normal control, 4 data points out of the 25 points were significantly lower than the other data points. Which of the following represents an appropriate action for the data represented by these points? Please select the single best answer. 1. These data points should be discarded as they are random. 2. Evaluate analytic procedures for an analytical problem. 3. Include the points in the data calculations. 4. Adjust ranges based on these low data points. Feedback. As required, the new control material was evaluated with routine analytical runs. This allows for the inclusion of all normal and acceptable variations inherent in the test system. The number of collected data points was appropriate. The greater the number of data points collected, the greater the representation of the true quality control values for the individual analytical system. Compiled data should be reviewed in its entirety. Data that is an outlier to most data points should not be eliminated. However, ranges should not be calculated based solely on these low points. All valid data points should be included in calculations. This allows the resulting data to reflect the actual test system variability. Upon review, if more than 2 data points appear to be significantly higher or lower than the majority of the data, this could be indicative of a potential analytical problem. Before finalizing the control ranges, the problem should be resolved. Thank you for watching. Follow part 3 to discuss the quality control rules. Don't forget to like, share, subscribe. See you next video.